Welcome everybody to the last seminar of the semester. This is the seminar of the Latin American Network on electromagnetic effects in strongly interacting matter. And today we have the pleasure to have Jinfeng Liao from, I hope I have pronounced your name, okay.
No, you're totally fine.
From Indiana University, talking to us about spin transport and the chiral-magnetic effect in heavy ion collisions, just giving a very brief introduction of our speaker. Jinfeng got his bachelor and master from Tsinghua University. He got his PhD in 2008 in Stony Brook. Then he was a postdoctoral fellow in Lawrence Berkeley National Lab, research associate in Brookhaven, and then he entered in Indiana University as assistant professor, then associate professor, and since 2021, he's been full professor at Indiana University. So he got several honors and awards, RHIC Fellow, Individual Research Award from the Institute for Advanced Study, Max Dresden Prize, DNTM Prize by Stony Brook. He was also distinguished graduate, so since his master from Tsinghua University. And he got this recognition as very excellent by the European Physical Journal and Nuclear Physics A. He has taught several courses and he's been author and co-author of over 120 research papers with an 8 index of 40. So he's a very recognized person in our community. I welcome you, Jinfeng. Thank you again for accepting our invitation, and please go ahead.
Thank you, Alan, for this very kind invitation, and I'm so happy to be able to connect with many of you. Unfortunately, last year I think there was a workshop that I wasn't able to make it, but I'm glad now we can discuss some physics together online. Can you hear me clearly? Everything good?
Yes, I hear you very clearly.
Okay, good. All right. So I'm going to talk a little bit about the spin transport and then the chiral-magnetic effect in heavy ion collision. So here is a plan of my talk. Again, with a little bit general discussion of spin transport, and then I will focus more on the chirality and chiral-magnetic effect, especially the search for this effect in heavy ion collision. So a little bit of introduction. I'm sure the audience here are all quite familiar with our field in general, the heavy ion collision and the strong field effect and so on. Our field in a way fit very well with the theme or slogan from APS April meeting. If you ever went to one, it is about from quarks to cosmos, and indeed. What we do research about essentially is about a situation where the cosmos is exactly the same as a hot quark and gluon soup. So that was in the early universe. We know that back then the temperature was so high that there are no individual hadron. There will be a plasma of quarks and gluon. So that's what interests us in the field in general. How do we do that? I mean, that was long gone. That was many billions of years ago. Today, we achieve that by recreating this state of matter using heavy ion collision at the relativistic heavy ion collider and also the Large Hadron Collider. These are perhaps the only ways for us to replicate and to study the early universe environment. So let's sort of like yesterday once more. Some of you were at a similar age to me or even older would know this song. So it's a very nice song. But what we're doing essentially, like using the needle bound, the heavy ion collision to create the yesterday once more. All right. So what have we learned? RHIC started in 2000, and I think RHIC started 2007 or so. So it's about a 20 years span of these really high energy nuclear collision. So what do we have learned? Well, in the last 20 years or so, I think a lot of attention have been mostly focused on the energy momentum transport in this system that you create in those collisions. And a big discovery was, of course, that how does that QGP or quark-gluon plane behave? And the answer is that it's a nearly perfect fluid with a very, very minimal shear viscosity over entropy density ratio. It also can propagate all kinds of ripples from either an initial condition or a penetrating jet through the fluid. Many of those subtle effects have been observed. But all these studies are mostly focusing on the transport of energy and momentum in such a many-body fluid. It's only in the last several years that people start to shift or start to pay attention to the spin degree of freedom in the fluid. Remember, quarks and gluons, they are some of the fundamental particles in our standard model, and they're both with spins. Quark has spin 1/2 and gluon has spin 1. So there are really a lot of spin degrees of freedom in the fluid. So this is really kind of opening a new angle of looking at this system we create in heavy ion collision, namely to look at the spin transport in a quantum fluid. So that's what I want to discuss a little bit in my introduction. I think this is exciting because really that, this is a degree of freedom that we don't fully understand to every detail yet. It's different from the energy momentum transport, which I think we understand to a very good extent. So what can I do with spin? Well, imagine that you have a heavy ion collision, you create a system with many, many little spins of each individual particles. You can do a lot with them. Actually, fortunately, we do have a few ways to probe those spin degrees of freedom. And I call this like the polarization effect. There's different type of polarization that you can look at. You can use chirality, or you can check the chirality polarization, which means if your system, especially with the quarks, if they are having a chirality imbalance, meaning that your left and right-handed particles are not equal, then you would have a chirality polarization, and that leads to a correlation between momentum and spin in the system. You could think about rotational polarization. If your system is rotating with the angular momentum, then it turns out that spin can also be polarized along that rotation. And of course, the more familiar example would be the magnetic field. This is very well known, of course, in condensed matter atomic physics from more than 100 years ago, that if you apply a magnetic field for a charged particle like a quark, charged fermion, their spin will be polarized. So with all these different ways to play with spin, actually we can we have the opportunity to observe many novel phenomena in this heavy ion collision system. I will give you a few examples about why this physics is interesting, and then I will focus on particularly the current magnetic effect, which is a joint effect of both the chirality polarization and the magnetic polarization. Okay, so one thing I want to point out that, of course, is that our heavy ion collision system, as I already mentioned, that carry a large angular momentum. And that's actually was known from a while ago. If you think about a typical line central collision like this, so this is the beam direction, this is the transverse direction. If their central mass of the two nuclei are mismatched by an impact parameter, it's very easy to calculate the whole system carry a large angular momentum to start with. So this is a very simple pocket formula. You can see if you do an estimate for something relevant to RHIC or RHC, it can be easily reaching 10 to the 4 to 5, h bar, which is huge for a subatomic system. It was suggested, like by Liao and Wang back in 2005, that this large orbital angular momentum of the system can turn into spin polarization effect via platonic cross collision processes. And there was a very nice study actually by Giorgio and collaborators, Barbara and Miklos, shortly after that, which gave the first perhaps quantitative assessment of this effect. Actually, that was studied all this in quite a detailed aspect, and also including a first evaluation of those vorticity. Later on, Beccatilli and collaborators built a fluid dynamical scenario. This is more the kind of picture we look at this phenomenon today. Namely, your angular momentum will turn into fluid vorticity and then that polarized spin. This is like a thermal model formula for that phenomenon. I'll come to this a little more soon. So, but if you come back here and ask, even though this is a big angular momentum that you start with, That all of that angular momentum, propagated to the fireball itself. This is a question that, of course, is not totally clear. I think in their paper here, they had some calculations on that. So I got interested in this problem. I want to figure out how much rotation you really have in the collision system. What that means is that, of course, in a heavy-ion collision, a lot of those nuclei in your nuclei would be just spectators. They will pass by, and then they will take away a lot of the angular momentum that you have. So what matters for experiment would be the angular momentum that stay in the fireball that you created at mid centrality. Mid rapidity, sorry, yeah. I, with collaborator, we did a calculation, basically trying to answer a question like what fraction would stay in the fireball, and if that fireball angular momentum conserved with time, and how the hot fluid would accommodate this angular momentum. And we had a detailed understanding of those processes. It turns out that there are only up to about 20% of that angular momentum that will stay. Of course, it's still a large angular momentum that you have in the system. Also, that angular momentum is basically conserved. So the fireball has to stay with that angular momentum. This fraction, of course, strongly also depends on collision energy. That's one thing that's important, because at high energy, actually, you have very little. And finally, how the fluid accommodate that angular momentum, that turns into all kinds of fluid vorticity patterns. And it's not like you have a rigid body rotation that everything is rotating around the axis. You have many local patterns of those vorticity. But if you average over the whole fireball that you're interested in, you can define an average vorticity of the system. And it turns out that vorticity, which quantify the kind of rotation effect in your system, is much bigger at no energy than high energy. Basically, the vorticity at order 10 GeV collision is much, much bigger than that at 100 GeV collision. And that turned out to be a very useful insight, because you may ask, what happens if you have a system that has non-zero vorticity? What's going to happen? Well, what's going to happen is the rotational polarization that I mentioned earlier. This was essentially studied some time ago in the solid state and known as the Barnett effect. In the context of fluid system, that's still being very, very enthusiastically studied in condensed matter system. Namely, if you have a fluid and you're letting it rotate, and that actually can polarize the electron spin. The physics is basically a macroscopic rotation with global angular momentum will align the microscopic spin of your particles in the system. If you do have that, then this vorticity that you have in the quark-gluon plus or whatever QCD fluid you create should lead to a polarization effect of the spin. And indeed, that has been observed, and that was quite exciting. Back in 2017, STAR reported their measurement of that polarization effect of a particle called hyperon, and you could see a clear signal that is becoming much bigger at 10 GeV order collision. Various calculations, modeling described that behavior pretty well. And that allowed people to extract an estimate of the average vorticity, which is about 10 to the 21 to 22 per second. And that got us the name that's the most vertical fluid, which of course is something new in the last several years. So that also triggered a large interest in this topic, which I mentioned earlier, namely the spin transport in general in this heavy-ion collision system. We do see that there are vorticity structure, there are angular momentum, and that can turn into spin polarization. So what happened to spin become certainly a very, very interesting topic in general. Those measurements in the last couple of years have been pushed further. For example, measurements down in the Nature paper of STAR was down to about 7.7 GeV, and now that has been pushed by both the STAR beam scan program and the Hades experiment down to a few GeV range. And surprisingly, you can see that spin polarization effect become even stronger in that order 1 GeV energy regime. Another latest result was from STAR again, which was published in Nature 2023 earlier this year. It was a measurement of the similar polarization effect for different type of particle, the vector meson. You could see that for the fine meson, they see a very large signal going from almost zero at high energy to very large at no energy. I want to emphasize that this is a really large signal. This is also a really large signal. I don't think we have completely understood the implications of those measurements yet. So, but I guess this is enough to tell you that it's very actually interesting and exciting at this point to understand what exactly happened to spin degrees of freedom in our heavy ion collision system. What spin can do? There are many interesting effects or phenomena that can happen because of the spin. For example, we know that a lot of our interest from heavy ion community is about the phase structures, like does chiral symmetry restore? What kind of phase you have at a given temperature and density. Here the question is, can phase structure be influenced by spin degrees of freedom? And the answer is yes. Especially, we know that there are pairing phenomena involving fermions. In our case, of course, fermions at quark. There are many examples. You have chiral condensate in the QCD vacuum right away, which is essentially the pairing between quark and anti-quark in a specific channel. At a very high density and low temperature, we potentially have a diquark color superconductivity, which is the pairing between quark and quark. Some people also propose that at high isospin density, you could get non-trivial, mesonic superfluidity, like a pion superfluidity, and so on. So here's the question that if you take into account spin degrees of freedom, actually phase structure can be changed under rotation. Take the chiral condensate as an example. Chiral condensate that's what we call the sigma channel, where you have a quark and anti-quark. If you look into the detailed structure of the spins, it's such that their spins are aligned, where their orbital angular momentum is the opposite to spin, so that they add up to a angular momentum zero state, a scalar pairing. But if you do have a rotation in the system, like the system we have in heavy ion collision, or the system in the neutron star, like in the pulsar, that strong rotation actually tend to align all the angular momentum. Again, this is the rotational polarization effect that I mentioned earlier. So all the angular momentum, the orbital, the spin are subject to that polarization. So as a result of that, this pairing will be suppressed. So this is the rotational suppression of scalar pairing. And indeed, if you do a calculation with effective model like a GL model, you would see clearly that effect. In a rotating system, your chiral condensate at all temperature would be suppressed by a rotation. And of course, if you turn it around, you'll say, okay, we do have particles or mesonic structure that have finite angular momentum. And indeed, the answer is that the rotation can enhance some of them. For example, by using similar model, effective model, you can show that there's the rotational enhancement of rho condensation, which has angular momentum 1 at high spin density due to the rotation. So, so you can see these examples clearly demonstrate that your phase structure can be influenced by external condition like rotation due to the spin degrees of freedom. There are other interesting questions that you can ask about spin. For example, what happened to the hydrodynamics if you have a system with spin and in general with angular momentum? If you think about fluid dynamics or hydrodynamics, what you're doing here is that you say you have a large macroscopic system, which are varying over some large known time and known distance scale. You have all those hydrodynamic fields or variables vary over that macroscopic scale. On microscopic level, you have what we call the fluid cells. And those fluid cells are close to local equilibrium, and then they can exchange momentum energy with next cell, that need to this transport described by hydrodynamics. And of course, the ultimate law is the conservation of energy, momentum, and so on, and conserve charge. Now you have a new player, because if you think about space-time symmetry of our fundamental physics, there are not many. There is, of course, the energy conservation and energy momentum conservation in general, and then the other would be the angular momentum conservation. Okay, so if you have a fluid and you throw some angular momentum in, just like what we have in the heavy ion collision, you ask how those angular moments are going to be transported around your system. In a way, this is more like a spin physics of a fluid cell. Okay, remember that spin physics is often talked about for a proton. A proton, in a way, it's just a collection of quarks and gluons, quark, anti-quark, and gluon. So people ask, if you gave that system a half h bar, a angular momentum, what happened to that half h bar? How you divide them into different pieces? Here is the same thing. We have a heavy ion collision, fluid. We throw thousands of h bar of angular momentum in the system. what happened to that, that angular momentum. So in our case, it's natural to think about, a hydrodynamic description. In that case, of course, in addition to your normal T mu nu and N mu, you would have a angular momentum current that need to be conserved. And that angular momentum is associated with the fluid cell over that, scale. With respect to the global frame, there's a trivial part. That's when the fluid cell moves the whole with respect to the global frame. So this is a trivial orbital angular momentum contribution. But then there is the intrinsic angular momentum of that fluid cell. There are many conceptual questions that one can ask, like, out of this whole angular momentum, how that is divided, among the orbital motion within your fluid cell and spins of individual particles, and how you do a gradient expansion and develop viscous hydrodynamics for a system like that, for this term in particular. How can you use that for phenomenological modeling, like calculating, spin polarization that I mentioned earlier? So these are all interesting questions. There are many, many progress that in the field in the last couple of years. Of course, I don't have time to discuss all the detail, but just to kind of pose the question here that, a lot of people are thinking about hydrodynamics with angular momentum or with spin transport. You can also think about another description of a many-body system, and that's quantum kinetic theory with spin. Again, spin is intrinsically quantum degrees freedom. So any description of spin transport would have to be, quantum. So basically, you can use quantum kinetic theory that had been developed a long time ago, but now it had kind of renewed interest in our field because of all the recent progress with the spin and chirality. One possible example is, say, you start with a Weyl function formalism, which include all the different components pertaining to different degrees of freedom in your system. You have, vector current, axial current, you have your spin part and everything. Or you can just directly start from quantum field theory to do this similar, study. But in short, so there are many interesting questions also in the quantum kinetic description when you have spin degrees freedom. Just to give you an interesting example, let's think about, for example, chiral fermion. Chiral fermion, I'm going to come to the chiral fermion soon. But for now, let's say just focus on one thing. That is that a chiral fermion has spin and momentum that are aligned. Let's say, suppose it's a right-handed fermion like this, like an antineutrino, for example. So if you think about the Lorentz transformation of a chiral fermion, is actually quite interesting because there's going to be a clash of Lorentz covariance between the spin and the momentum. On one hand, you say this momentum is the Lorentz 4 vector, of course, when you transform it. On the other hand, spin belongs to the angular momentum, which is not a 4 vector. But on the other hand, the chirality is the Lorentz invariant property, meaning that when you transform into another frame, your right-handed chiral fermion is still a right-handed chiral fermion. So how you reconcile them? That's not a trivial question, and that's actually the answer to that at a kind of ad hoc level. Is that the fermion need to go through what people call a side jump, discussed first by these gentlemen, meaning that you actually have to make up the spin has to follow momentum. So the angular momentum need to be made up by a additional orbital contribution when the particle has what we call a side jump. So this is an interesting example to tell you that when you have spin in the system, even the simplest quantum kinetic theory become kind of non-trivial. And we showed exactly from this Wegener formalism in this paper, we showed exactly when this happened, why you need that side jump, and that's because that clash of Lorentz covariance between the two. So I hope that I give you a really quick kind of tour that there are many interesting things when you have spin degrees freedom in the system, and many questions that both conceptual and phenomenological questions that can be studied. So actually about 2 years ago, we actually published a volume of book. Many of those chapters are available in the archive, basically focusing on discussing this different kind of questions associated with the spin transport in heavy ion collision. And out of all those different physics that you can do with the spin transport in heavy ion collision, I'm going to focus next on the chirality and the chiromagnetic effect. So that's really the chirality polarization I mentioned at the beginning. Before I go forward, any question that you may have?
Any questions? We'll leave it to the end.
Okay, sure. Yeah, and I just want to say that if you have a question, feel free to interrupt me. Well, let's then move on to the next part of my talk, which is about this chiral-magnetic effect. I'm sure you all have heard about it and perhaps heard many talks about it. So I'm going to be brief here. I mostly want to discuss what we know at this point about the search of that effect in heavy-ion collision. So the concept of spin and chirality is well known, in textbook for Dirac fermion in general, and in the massless limit, of course, you can split into left and right-handed sectors. I'm being a little sloppy here in not differentiating the chirality and helicity, but for a particle, that'd be the right picture. You have a right-handed fermion with spin momentum correlated in the parallel, and for left-handed fermion to be anti-parallel. So there is a classical symmetry associated with that, that's axial symmetry. If you look at this Dirac Lagrangian, you'll know that the mass term, if you add a mass term, of course, that's spoil this specific correlation between spin and momentum, because that mass term will mix left with right. This is all well known. And if you look at the axial current that is classically conserved, you get this mass contribution to that current, violating that current conservation. In QCD, the mass for the quark, of course, we are focusing on quark, is a little tricky because you have a constituent mass, which is the contribution of the standard model mass plus the non-perturbative chiral condensate contribution. So in that sense, this is much larger than the standard model mass for our light quarks. So really that you don't have anything that I just mentioned here because of that chiral condensate. However, we are dealing with the high temperature phase of that system. We're doing heavy-ion collision with temperature reaching a very high temperature, so that chiral condensate will melt away. Then we are very close to a chiral limit. So that's one thing that I want to emphasize here, that if you're in a quark-gluon path with this term gone, then you are in a good position to explore the chiral effect associated with quark. So another interesting effect that we know very well is the chiral anomaly. So even if you have perfectly chiral restored phase, you have quarks that are nearly chiral, that axial current is still being broken because of that triangle anomaly. And again, this is all very well known physics. The new physics that associated with the chiral-magnetic effect is the following. We know that any microscopic symmetry has the implication for macroscopic matter property. For example, you have space-time translation invariance, then you have the conservation of energy momentum on macroscopic level, you have your hydrodynamics. So here's the question: if you have a microscopic anomaly, which is only a semi-symmetry, if you wish, what is the implication of that for macroscopic matter property? And that was figured out a while ago. Namely, they will induce what we call the anomalous transport in general, so anomaly-driven transport, so to say. In the case of chiral-magnetic effect, that basically says that if you do have a system of chiral fermion, and that system is chiral in the sense that the right-handed and left-handed particles are not equal in numbers, so that you have a finite, what we call axial charge on mu5 or n5, and you apply a magnetic field, you will get a transport of electric current. Okay, so this apparently is a quantum mechanical effect. It's a transport effect due to the spin degree of freedom and the chirality. Not only that, this coefficient is fixed totally by the anomaly itself. So that's an interesting effect. You can see it's different from any other normal transporter. In the normal transporter world, you say you apply or you turn on an electric field, you get a current. Now this is different. You turn on a magnetic field, you get a current. To explain a little bit, just to kind of have an intuitive understanding of this effect, I would like to use the polarization picture I mentioned earlier. So this is really a interplay of magnetic polarization and chirality polarization. So let's start by thinking about a system charged quark. That's it. For simplicity, consider only positive charged quark. You apply a magnetic field, what will happen? Well, their spin are going to be parallel, or more preferably parallel to the B field. That's the magnetic polarization. You have more spin up than spin down. Now, if your system is also chiral, meaning that you have more, say, right-handed than left-handed, that means your momentum of the quark is preferably along the spin direction. You combine these two polarization effects, together, you say, okay, momentum of quarks is parallel to spin. Spin is parallel to B field. Then you get a motion of those charged quarks along the magnetic field. And that, of course, is an electric current. So you can see in this picture, the CME can be interpreted as just a joint effect of magnetic polarization and correlated polarization. Of course, that argument cannot fake this coefficient. This coefficient really comes from the anomaly itself. Okay, so why we are interested in that? In the heavy-ion collision, of course, there are several reasons. So one of the reasons that I already kind of mentioned, namely that allowed us to test some of the chiral effect, because we're in a chiral restored phase and we want to see evidence of that. And this certainly is the effect that happened only in the chiral restored phase. And the other important reason is associated with this mu5. I mentioned this is the difference or imbalance between right-handed and left-handed quarks in our system, but where does that come from? That arises from the gluon topological fluctuation. So let's get really interesting. We all know that, you know, in QCD and in non-abelian gauge theory in general, configurations of gauge field with non-trivial topological configurations, you know, are important. For example, for chiral symmetry, you know, breaking, or confinement, for many other effects. These objects, such as the incident and spin-around, they are basically configurations with that trace the color orientation of your you know, gauge field around space-time boundary. So that's how it arrives. So you use this so-called topological winding number to characterize those aspects. This Q of W, the winding number, essentially like a E dot B, if you wish. And you can see that that naturally need to consequence for the fermions, because if you integrate that give you what we call the basically the this important equation here. Every unit of topological winding will give you twice the difference between right and left-handed quarks in your system. This is called a single index theorem in a more broader context. You know, in the context of gauge field, what happens is like this Mobius stripe. That's your gauge field configuration. When you couple fermion to that gauge field configuration, the fermions are like the ants, you know, moving along that gauge field configuration. When they move one, you know, loop, they actually go from the inside to the outside, which means, in our case, means that you go from left hand to right hand. So that net chirality in our colliding system arises from the topological fluctuation, and of course, we have the chiral stream restoration. So that means that, you know, if you are able to observe this effect, that will give us access to those fundamental physics like the chiral symmetry restoration and also the topological fluctuation of gauge field, like gluon field. There are more than just, of course, chiral magnetic effect. For example, there are various effects that have been proposed, like the so-called chiral separation effect, chiral electric separation effect, chiral vertical effect, and so on. For this talk, I don't have time to discuss all of those, so I'm going to focus on just the chiral magnetic effect. I also want to point out that there are strong interdisciplinary interests in this effect. For example, people study the effect in condensed matter system, in astrophysics, in cosmology, plasma physics, quantum information even, and also broadly in the quantum field theory and mind-body theory. So, so many interest in this effect. For us in the heavy-ion community, so these are some of the references if you want to find out more, because I don't have time to discuss all this. So there are many reviewed in the recent years on this topic. I'm going to focus on one big question. Can we see this effect? Namely, can we find CME in heavy-ion collision? Well, this obviously is an important question. And we have been trying to give an answer over the last, I don't know, 15 years. I think it started with the initial idea from Dima Kajeev, many of you know him. There were this couple of early papers, 2004, 2007, 2008, with various collaborators. Those essentially laid the foundation for the search of CME in the heavy-ion collision system. So of course, there is a question of how exactly you want to look for it. Suppose you're convinced that this effect should occur in heavy-ion collision. How should we look for it? What kind of observable we can use? So that was the other paper by Sergei Voloshin, also shortly after DMAT paper. He proposed a specific correlator which now became famous, the so-called gamma correlator, which is basically a two-particle angular correlation in the heavy ion collision system. I'm going to explain a little more about this later, but for now, I would just want to mention that this is the main observable. There are a number of a variation of that observable, but the basic idea is based on this two-particle correlation. So what exactly is that signal? Well, that depends on first how paramagnetic effect would occur in our colliding system. So this is a three-dimensional cartoon of our colliding system. You collide, and there are those spectators that fly away, and then there is a fireball that's created in the middle. So when they start to overlap the two initial nuclei, because they are positively charged, they have a large Z. For example, for gold, this is 79. It's a large positive charge, and they're moving fast. They're moving at nearly the speed of light. So there's a very strong magnetic field associated with both nuclei, and especially when they're overlapping, those two individual magnetic fields, they add up to give you a very strong magnetic field in the middle. So you can quickly estimate that, based on very simple electrodynamics, classical electrodynamics. So that's how you can estimate it. If you plug in numbers, you'll get something like this. That translates into something on the order of 10 to the 15 Tesla. Well, obviously, this is way bigger than any other magnetic field we know, even from magletar. So it's perhaps the most, the strongest magnetic field you can have. So this is a more, dedicated, Monte Carlo simulation of that magnetic field based on many thousands of events. You can see if you average over events, that magnetic field is relatively homogeneous. So this is where the fireball is created. In that middle part, the magnetic field is basically on the order of that 10 to the 15 Tesla, and it's relatively homogeneous. However, I do want to mention that many people know that magnetic field may be short-lived because those spectator ions, which contributed the majority of that magnetic field, would quickly fly away from the collision zone. So that's the big question or uncertainty for that magnetic field. Namely, how long does it live in the fireball? There are people who argue that medium effect would, allow that magnetic field to live longer. But again, we don't have a definitive answer. But we do know that the system starts with a very strong magnetic field at the beginning. Okay, not only that you have a magnetic field that is strong, actually the direction of that you can see has a almost definitive direction. If you look at this average picture, it's pointing right in the y direction, what we call the outplane direction. But if you look in a little bit more into the details, you will realize that on an event by event basis, actually due to the fluctuation of the initial condition, that magnetic field actually is not always perfectly pointing up. Actually, it's pointing in all directions. So these are some of the simulations that we did a while ago, actually 10 years ago. We were perhaps the first to point out that actually there's a strong fluctuation of the magnetic field orientation, even though on average it's pointing in the y direction. Event-wise, it actually has a wild fluctuation in the angle. And that angle is correlated with your second order event plane, namely the so-called elliptic flow direction. But that correlation has a finite weight, and also that the strength of that correlation depends on centrality. So it's not always perfectly aligned. It actually has some correlation or decorrelation, if you wish, between magnetic field and the colliding system geometry. So that turned out to be an important feature later on. So these are some of the quantitative calculation of those correlators between the magnetic field direction and your harmonic flow plane. Okay, so I'm not going into details. I only want to say that you do have this important fluctuation and correlation effect, and that turns out to be a valuable feature for validating that B field signal later on. So what are exactly the signals? So if you do have a B field approximately in this direction, that induced a transport current through the chiromagnetic effect. Okay, that means your positive charge starts to flow up, your negative charge starts to flow down. So that creates a little dipole in your fireball. And then the fireball itself explodes out just like a bomb. What happens is that, excessive or extra positive charge on the top will be blown out this way, while extra negative charge on the bottom will be blown out this way. So that information turned into the momentum dipole in the final state observable. When you what you measure at the end of a heavy ion collision are the momentum distribution of those particles. So the prediction is that you have, preferably positive charge emitted in one direction and preferably negative charge emitted in the opposite direction. This is the two-dimensional representation of the same story. So basically, we're looking for a specific emission pattern of charged particles along the magnetic field direction, which in our case is, for which we use the event plane as a proxy. Okay. Same sign hadron emitted side by side, opposite sign hadron emitted back to back. That's what we're looking for. Have we seen the CME? That's the big question. Well, the first measurement start announced by Star in 2009, and in the last 13, 14 years, huge efforts were made by all the different collaborations, Star, ALICE, CMS, and RHIC, and RHIC. The search was done from beam energy down to 10 GeV all the way to 5,000 GeV beam energy. People look at various colliding systems, PA, DA, kappa, kappa, gold, gold, uranium, lead, and now actually adding also the isobar system, which I'm going to talk about in a moment. It proved to be a very difficult search. The main reason for that, it took us like some 5 years or so to understand that because we're facing a situation where there's a very small signal contaminated by a very strong background correlation. Okay, there are two major backgrounds in this measurement. One of them is the resonance decay. The other is what we call a hydrodynamic effect that we call local charge conservation. In both cases, what happens is that you have little, neutral cluster that decay into charged particles, positive, negative. For example, if this is a rho meson, rho zero meson, it will decay a pi plus and pi minus, because they both carry some of the momentum of the initial parent particle. So they will have a co-moving correlation, a positive charge and negative charge with a co-moving correlation. Similarly, in the local charge conservation case, if you have a fluid cell which is charge neutral and is moving, and then you turn into particle with positive and negative charges that are correlating their direction of motion. Why that would cause trouble? Because that effect is stronger in plane than out plane. So when you measure difference between in plane and out plane, you will pick up effect from this. Where our signal is also trying to pick up a difference between in plane and out plane, because out plane is what we call the B field direction. So we're looking for that pattern stronger in this direction, where this effect can also create a kind of fake difference between in plane and out plane. And that effect is scaled roughly like a V2 over N. N is the total multiplicity, and a V2 is that difference between in plane and out plane, the elliptic flow. So after that, after a few years, we started to redefine the question. We're trying to extract or constrain the fraction of CME signal within the measured correlation. Well, you have a measured correlation, two-party correlation, the gamma correlator. Out of this gamma, what fraction is the CME contribution? What fraction is the background contribution? Of course, we already know this is way much smaller than this, but still, the question is that, is it finite? That's the big question we want to answer. And you should realize that we're not alone, because if you think about many other famous searches, all this, it's always like a very small signal, tiny signal in a big background. You have to fight with that. Many methods or strategies were developed, in particular, this based on the two-component decomposition. Your CME signal is driven by the magnetic field. Your background is driven by the bulk elliptic flow, as I explained here. Flow drive that effect. So there are various approaches, mainly trying to do a contrast method. For example, you can vary the bulk flow by fixing the magnetic field. So this is something we call event shape analysis. You can vary the magnetic field for fixed bulk flow. So that's the isobar collision I'm going to talk about. You can vary B and the bulk flow in opposite direction, making one bigger, the other smaller. And if your signal should respond to that. So this is what we call the event plane versus spectator plane method. You can use this small colliding system to constrain background, because these are systems where we don't expect CME. So there are all these different approaches. We also, these are mostly, of course, experimental approaches. You're trying to, separate those two. We're also developing theoretical tools for quantitatively, and realistic understanding both of the signals and the backgrounds. roughly before the isobar collision results that were released in 2021, that's essentially where we stood. We had some hint of the possible signal of that correlation that may belong to CME, but we're not very confident because the confidence level is relatively low. We cannot make a conclusion. So that's why a number of people in the field pushed for a isobar collision experiment. So that idea started around initially with a suggestion from Voloshin, and then there were a lot of discussions in the subsequent years. So in 2016, there was a task force that recommended doing this. Okay. So what they are going to do, what their plan was to collide two different nuclei, the ruthenium and zirconium. They have essentially the same nucleon number, so that the created fireball would be very, very similar, if not identical. But their nuclear charges are different by 10%. So that magnetic field will be different by 10%. The hope is that that will give enough of a difference between the two systems. Again, so here is the idea in a more quantitative way. You have the magnetic field difference, actually the magnetic field square, because this is what controls that correlation strength of the CME signal. They differ by about 15–20%, where the eccentricity difference between the two systems would drive or determine the background will be almost like very little. So here is the cartoon of what you're expecting. You know, you have an identical background between two systems, a mild difference between the signal. Depending on the signal to background ratio, you could have a measurable difference between the ruthenium and zirconium in the total correlation you measure. Okay, so that's the strategy. Does it work? Well, I'm going to tell you in a moment. So meanwhile, you know, thanks to the Beam scan theory collaboration, we were able to develop a quantitative tool, which is what we call the event-by-event anomalous viscous fluid dynamics simulation model that allowed us to do quantitative calculations for both the CME signal and also related background in the context of heavy ion simulation. Also, people took a deep dive into the observables. As I mentioned, there were different ways you can kind of vary background, you vary B field, vary flow, or vary both. You know, several observables were proposed based on the gamma correlator, and people, including us, took a deep dive into that, trying to understand how those different observables will respond to your, you know, your measurement control. Okay, so one of the issues that it eventually turned out to be important is certainly about the initial condition of your heavy ion collision. It's in particular about the nuclear structure input. Namely, you see, there was a big assumption. Namely, the background between the two systems would be identical. Even back in 2017, 2018, in particular, there were people that were raising concerns about this assumption, including Fuqiang Wang and collaborators, including our group, and also Hannah and collaborators. We realized that, you know, there are some uncertainty about ruthenium and zirconium system. Their nucleus are not exactly the same. Nuclear structure is a very complicated. Actually, even today, people are still trying to solve those things. So if you take what we know about those ruthenium and zirconium, or any theoretical model calculation, you will see that there are some difference in the nuclear structure between them. So the question is, could this mess up with the isobar contrast? And so of course, several groups did calculation that suggest that there could be some issues, namely your background could differ on the order of few percent, and you want to remedy that. Actually, we even suggest a strategy to do that. Namely, you want to take, you know, instead of doing the usual centrality dependence, you want to really apply joint multiplicity and elliptic flow cut so that you compare ruthenium zirconium system at the same multiplicity and at the same, you know, elliptic flow. That's what I talked about at Quark Matter 2018 in Venice. Later on, we also published a paper with the prediction for isobar collision based on our simulation tool, and also based on the strategy that I just mentioned. Namely, you want to make them to be identical before you compare them. All right, so these are now, of course, they're all history. So
In 2021, so the data were taken in 2018. And after a few years, there were various reasons why that took so long, and there was a pandemic in the middle. So in September 2021, STAR finally released the result for the chiral magnetic search with the isobar collision. The predefined criteria according to STAR was that your correlation in the ruthenium should be greater than that in the zirconium for the reason that I just mentioned. Namely, identical background, 20% larger signal in the ruthenium due to the stronger magnetic field. So that was the criteria for CME. It turned out all those different measurements methods by 5 different groups, they all consistently gave a result that's below 1. So if you are above 1, you say there's a signal. If you're at 1, you say there's pure background. What does it mean even if you have a result below 1? So that was quite a surprise. That I'm sure was a surprise to them. When we saw the results that were released, of course, that was a surprise to us too. And obviously, this cannot make sense, just in a straightforward way. So what happened? Well, if you look into that STAR paper, actually there are a lot of measurement detail that actually immediately tell you the answer. What was the trouble? The trouble was that field assumption. As I said, if you're assuming the background to be identical, then that's what you would expect. But if the background do differ by a few percent, then that's a field assumption. You look at the V2 measurement, uniform flow, and then multiplicity measurement in the same centrality. That's the centrality is what STAR used to compare the two systems. Namely, you're comparing two systems in the so-called same centrality. And the answer is that you do see a few percent level of difference in both the uniform flow and in the multiplicity. Okay, so remember that the key for success of this isobar contrast was the identical bulk between them, and that was not the case. And that explained why you didn't see anything above 1 or even at 1. You see all of them below 1. That simply means the background between the two systems is not equal. You actually have a much bigger background contribution in the zirconium. That makes this ratio to be below 1. So in the STAR paper, it said that significant differences in the multiplicity and flow are observed between the two systems. That basically means that the assumption was failed. And then they say no CME signature that satisfied the predefined criteria had been observed. And this is a very, very confusing sentence, especially if you only look into this one sentence at the end. So really what happened is that the predefined criteria is not applicable, meaning that this is not supposed to be used here. So really you cannot make a clear conclusion about that signature because your assumption is not right. Your predefined criteria is not right, okay? So what can you do? The real question then is like, where is the baseline? When you want to compare ruthenium and zirconium, if you have a pure background, what that ratio should be? If there's 0 CME, no CME at all, where is that baseline? Previously, it was assumed to be at 1. And now, well, first, people understand this should not be at 1. Because, for example, if you look at the ratio of the multiplicity between the two systems, that means, for example, if you look at 40 to 50% of the collision for both ruthenium and zirconium, their multiplicity differ by 6%. You look at this. So if you remember, I mentioned earlier that the background scale like 1/n. So that explains why these are all below 1, because ruthenium, zirconium multiplicity is different. Okay, zirconium has less multiplicity, so it has a bigger background. If you take that into account, actually STAR also published that multiplicity for the two systems. That baseline, the simple-minded baseline will be right here, 1/n. And then suddenly all points, data points are above the baseline. So that's a very, very good indication that something actually is there. Of course, you want to be more quantitative, more serious about this. So you can, 1/n is just a simple scaling argument. So we took it from there. We tried to carefully examine, what is the quantitative baseline you would expect. The first thing you want to do is that you want to use a nuclear structure input that would reproduce exactly that multiplicity difference between them. And that was we were able to do. Actually, several groups proposed the nuclear structure inputs in from nuclear structure inputs that would produce that correctly. And we did that too. So you can see now the calculated multiplicity ratio between the ruthenium and zirconium agrees very well with the experimental data. So that's the first step. So that means you take into account quantitatively that difference. And then we can compute the gamma correlator and also another relevant correlator, which is known as the delta correlator, which is also two-particle charge correlation. You can see that, you do that calculation, this blue line are the baseline if you assume 0 CME, and the red are for the 20 to 50% collision, the experimental results. You can see that actually there is exactly some space for CME signal. So we want to extract the fraction of that CME signal. So this is based on, again, that picture. You remember what we understand now is that background is not identical. So from ruthenium to the zirconium, the background become bigger by this factor. This is based on the our simulation, okay? And then the signal difference is also understood based on simulation. The signal of the ruthenium should multiply about like this factor to give you the signal in the zirconium. The difference is at this level. Sorry, this is actually, perhaps there is typo, 0.85. And then depending on signal to background ratio, the total ratio will depend on the signal fraction. So by comparing that total ratio with experimental data, you're able to extract this fraction of signal. That's what we obtain. So the signal fraction in the ruthenium is about 8.6%, 6.8%, plus minus 2.6% of uncertainty. And this uncertainty is coming from experimental measurement uncertainty, in the data statistical uncertainty, and also it doesn't take into account some of the unknown systematic uncertainty. Okay, but what you can see that here is that the big message here is that you do have a room for non-zero signal on that level, 6.8%. And of course, if you take into account the uncertainty, you may say this is something on the 2 sigma level of a signal, which is not good enough, but not bad at all. And I think there are similar messages from experimentalists who are also performing similar analysis of what exactly the implications are from the ESBO data from, for example, Purdue group, from BNL group. We all, I think, we are all on the same page. Namely, there is perhaps something on the order of 1 to 2 sigma level of signal in the isobar collision. But to really quantify that would require a very careful understanding of what people call the non-flow uncertainty involved in the analysis. And also there are more post-blind analysis results that are coming from STAR. So that brings me to the end of my talk. Here's a summary. I think I don't want to repeat that. I just want to say that it's certainly very interesting physics of the spin transporting in general and of the CME in particular. The physics is rich and fundamental. The search for that effect, such as CME in heavy ion collision, is of great importance, but very challenging. We do have a hint of a small signal on top of a large background. The isobar collision, I think, had attracted a lot of eyeballs in the last couple of years, and many people got a wrong impression that nothing was found and this was done. And that turned out not to be the case. Actually, there is a potential failure signal for CME on the order of 1 to 2 sigma level. So what's next? There are many things that are going on, actually, if for those of you who are not paying close attention to what's going on in this part of the field. One of the things I want to highlight here is the reanalysis of the gold-gold data with something like 2 billion events. And that actually or leverage an important effect, namely the magnetic field is fluctuating in each event. And that fluctuation caused a very interesting effect, namely the magnetic field is more correlated with spectator plane and less correlated with the event plane. Because of that, the signal between the two measurements will be different. And you utilize that, you can actually try to extract the signal by comparing the measurement with respect to the spectator plane and with respect to the event plane or participant plane. STAR was able to extract about 1 to 3 sigma level of CME signal in the gold-gold collision. So this was published recently by STAR. So that's the first, I think, a positive statement from STAR on that. There's a 1 to 3 sigma level of signal. Depending on, of course, that 1 to 3, that uncertainty is due to some of the non-flow, uncertainty. STAR is also working on the CME search at lower beam energy, like when you go down in beam energy, what will happen? And there are some preliminary data. I don't want to go into details, just want to that you know that there are still interesting activities going on here, searching for CME at no beam energy, because it's important to understand how that CME signal would vary when you change the beam energy. We have specific expectations based on CME. And there are also still CME search at high beam energy, at least to constrain that. For example, this is a very recent effort from some of the Alice physicists who try to use our tool, AVFD simulation, compared to the Alice measurements, trying to see how much, whether you still need some CME contribution or not in order to describe those data quantitatively. And their conclusion that you have perhaps the overwhelming local charge conservation on the order of 50 to 60%, but you still may require a small contribution of CME physics to fully account for those charge correlations. So what's next? Well, skipping all those things, these are just listing things that are going on that we expect to have some more news in the next several years. Perhaps the most important thing is that during the run from 2023 to 2025, we're expecting, or STAR is expecting, to take another big sample of gold-gold collision data on the order of 20 billion if everything goes right. And that can really push the extraction of CME signal to a very high sigma level, has that potential. So here is what we say that we want you to be aware of that, and that maybe we'll have a firm final conclusion about the CME search in 2027. So stay tuned. Thank you. I'll stop here.
Thank you very much for this very detailed review about those subjects. We now open for questions. Alejandro?
Thank you.
Thank
you. Yeah, this was a very nice talk and review. You touched upon many subjects and all of them very interesting. And I wanted to ask you about these last issues that you sort of touched upon, the low energy behavior of the chiral magnetic effect signal. But the energy that you're showing here is not that low. So in other words, 20 GeVs in the center of mass. I was wondering, you see, there must be, maybe this is just wishful thinking, but there must be a connection with these effects when you go to lower energy, which of course makes it very interesting, with the polarization that you mentioned at the beginning of both hyperons and perhaps vector mesons. The question that intrigues me has to do with the fact that as you push, when you measure polarization, as you push down in energy, you're also pushing down in the threshold for production of particles. So for instance, if you measure the spin polarization of lambdas at 1 GeV, you see to create a lambda, you're already perhaps even going below threshold. So the question that I wanted to ask you is there a way that you may imagine that the chiral separation of charges also has an influence both on the magnitude of the polarization of the lambda, say, which is just to take something in concrete as an example, and the anti-lambdas, which, as you showed at the beginning, also show discrepancies. This is an unfair question, I understand, but I'm trying to make connections between the main subject of your talk, which is of course the chiral magnetic effect, and also the low energy, studies in connection with the spin properties. Can you comment on this?
Sure. Thank you. First, thank you for your kind word, and thank you for this very thoughtful question. The CME, so here indeed, what I showed here are some measurements about CME at relatively not so low, but on the order of 20 GeV indeed. The main reason for them doing this was because they have some new capability of event plane determination, which works particularly well at those energies. So that allows them to have a better measurement of this effect. So they're trying to make those more quantitative. So, then coming to the question of CME at even lower energy. Actually, earlier I showed a plot that was based on beam energy scan 1 measurements. So this, you can see that one of the things that people look for in the case of CME that you probably want to see that effect to turn off at no energy, at no enough energy. Exactly which energy occurs, we're not sure. Because for the reason for that is that there are several reasons. One is that the magnetic field in general become less in the no energy. But of course, again, this is actually a subtle question. If you look at the magnetic field calculation, of course, at no energy, you would imagine this gamma factor become much smaller. So the B field strength, of course, will become much smaller. So whatever effect associated with the B field could become much smaller. Also,
but it lasts longer.
Correct. No, you're totally right. So that's the other thing I want to say. However, that lifetime become much longer potentially at low energy because it just takes longer for the whole collision to go through. And so it becomes subtle whether magnetic field would drive the CME to be smaller and smaller than no energy or not. So that's a big question mark. The other aspect is because like all those flow and jet quenching measurement, one would imagine that anything associated with the chiral restored quark-gluon plasma will go away if you go down to enough of no energy. So ultimately, CME probably will disappear. That doesn't mean that magnetic field will disappear. Doesn't mean the topological fluctuation will disappear. But it does suggest that the CME perhaps will turn off at some no energy. That's why people want also to understand what is the beam energy dependence of this effect. And now coming to your last part of your question related to spin polarization. Indeed, that's a very, very good question because here, if you look at those spin polarization measurements, it's really surprising that they become so big at almost near threshold. Indeed, you can see the collision beam energy is very, very close to 2 times the nucleon mass. So that's basically the threshold. So we know that down here right at a threshold, not everything should disappear. So it's really an interesting question. What happened, in this region with 1 GeV or 2 GeV beam energy? And is there any connection with the spin polarization and the chiral effect? I think that's a very good question. So for example, as you already mentioned, that there is a big difference between lambda and anti-lambda polarization. Could this be due to magnetic field? Some people argue that that could be the explanation, namely a magnetic field due to the finite magnetic moment of lambda and anti-lambda. If you do have magnetic field at no energy, then that can help explain a higher polarization for anti-lambda than the lambda. So some people argue that at no energy, the magnetic field live much longer, so actually can help explain this difference. That's certainly some possibility that has not been ruled out, and it's quite possible. So in that sense, magnetic field could still be strong even at no energy. Whether there is a connection between chirality and the spin polarization, some people argue that if you do have a finite chirality in the system, that can make additional contribution, for example, to the spin alignment. I don't have detailed comment on that, but that's certainly there is such a connection because in the end, chirality is just a correlation between spin and momentum, and that can certainly lead to certain polarization or spin alignment contribution. The spin alignment, which measures the spin fluctuation. The other thing I want to say that I'm totally in agreement with you that these are really, really surprising results because the energy available in each binary collision really is just barely enough to produce something like a hyperon. So I guess if these data points stand the test of time, then that means we really have to re-understand how the lambdas are produced in this really no energy regime and how they acquire that spin information. Because the angular momentum of that colliding system is a global property. Like the whole system had that angular momentum. But a hyperon, of course, typically is locally produced. So how you transfer that global momentum to a locally produced hyperon, that's a big question. Yeah.
Thank you. This helps to the ongoing discussion. I appreciate very much your answer.
Yeah, thank you.
More questions? Well, I have a few questions here, but more than everything, I'd like you to comment. I don't know, what is your confidence level on these simulations that calculate the background? Because, I mean, what is missing to say it's there or it's not there? You showed different calculations estimating this background for the isobar collisions. And for example, you showed one plot by, I think, Futian Wang, which you have, where you have results above 1 and below 1. I mean, considering, let's say, a new baseline, and you have results above and below. So I don't know what it means. So I mean, that's the way. But how far are you people who are looking for this to say that now I have a very robust background and I can correctly interpret this results from isobar collisions? So could you comment on that?
Sure. Yeah. So I think from your side, there are two aspects. So one aspect is about how much we understand those backgrounds in the theoretical sense. In the theoretical sense, I think people, including the experimentalists, we generally agree we understand how to simulate them. So remember, Heavy-ion collision had been going on for a while, and then even the hydrodynamic simulation had been pushed to be really, really good in the last 20 years. That's why we had this paper actually before the isobar collision. So from a theoretical point of view, if you do a simulation, we understand fairly well how much a local charge conservation would contribute to the background, and how much the resonance decay would contribute to the background. So those backgrounds are, I think, very well understood. So, but that's not all the story about heavy-ion measurements. So I understand that you're concerned by this plot, for example. So here, what are the uncertainty that got people still uncertain about it? And that's something they call the non-flow contribution. To put it simple, so we're always doing a measurement of a system with just a few thousand particles in heavy-ion. This uncertainty that we don't understand yet are mostly on the more measurement aspect. So you're measuring a few thousand particles, or in theory, we're simulating a hydrodynamic system. In reality, you're just measuring a bunch of thousand particles. Of course, we assume they're collective. We measure a flow, for example, elliptic flow. There are specific procedures to extract elliptic flow out of these thousands of hadrons by looking at the deformation of their momentum space distribution.
Yeah, sure.
If you have things like a mini jets, you have 20 mini jets in your system, that create particle correlation that will eventually propagate into your flow determination. So that's what the experimentalists call the line flow contribution. And something like a mini jets are typically also causing 3-particle correlation background. Those will propagate into the gamma correlation measurement, the CME correlation measurement. How much they influence that ratio, this number, is not fully understood. It's on the order of 1% level. We don't understand it up to the 1% level, but that 1% is enough to cause the confidence level to drop by a lot. So that's why experimentalists feel like we probably know by 1 to 2 sigma, but not 3, 4, 5 sigma. I don't know if that answers your question.
Yeah, sure.
Yeah.
Okay. Well, I have another question about the first part of the seminar. So you showed these results that say that rotation suppresses the Chiral condensate. How could that be reflected in in the final state or something, because I mean, if you expect like that high vorticity in the quark-gluon plasma, what is it? I mean, it means that you don't have Kerr condensate or what?
You mean like in a real like collision system, whether there is some observable effect or not?
Yeah.
That's of course a very good question. What we demonstrate, for example, what is demonstrated in this plot is really a theoretical calculation based on a mean field model. First, what you add is that you add the influence of rotation through a vorticity. You do see a substantial drop, but this again, if you want to ask quantitatively how much I would expect, you can see that depends on how large your vorticity would be. So if your vorticity is big, then you can see a substantial difference. Let's say take one of the curve, let's say 150 MeV. That's when quarks turn into hadrons.
Yes.
Your Kerr condensate can drop by a factor of 2 if you have, say, 0.4 GeV of vorticity. But unfortunately, in heavy-ion collision, the vorticity not that big. That's perhaps they're more closer to this end. So that's why we haven't really done any kind of phenomenological study to say what kind of effect you can measure in heavy-ion collision, because it's much more difficult to measure something, because our vorticity, if you remember, based on the hyperon polarization, it's perhaps on the order of tens of MeV. So that's still much smaller than what you would need to see a visible effect.
I see. So it should affect the critical temperature, but just a little bit, and it's not observable, perhaps.
You could change the critical temperature. So actually, in the paper, if you look into this paper, there is a plot of phase diagram on the omega t plane, the vorticity and the temperature plane. You could see the critical temperature. It's just like a magnetic catalysis. So the critical temperature will depend on the rotation. It's just that to see a considerable effect, you need the rotation to be really large.
Okay. Okay, so more questions? If not,
sorry.
Okay, Christian.
Sorry, Jinfeng. In this case, I think the rotational looks like it acts the same as a chemical potential.
You are totally correct. Actually, that's something we noticed. Like omega basically behave like a chemical potential for angular momentum.
So it's basically the same. It's a source, acts like an effective source of at some point of a chemical potential.
Yeah, it's like a chemical potential. It's like, for example, if you have a fermion like quark, right? You have spin up and down. So the energy would be differed by omega times the half and minus omega times the half. So it acts like a chemical potential pretty much. Yeah.
Okay.
Yeah.
Okay, thank you.
You're welcome.
If there are no more questions, let's thank the speaker again.
Thank you all for your time and
Okay.
I will stop recording now.